Hello, my name's Chris Svoboda. I'm from Michigan State University, and today we're going to look at pyroxenite as the source of Eocene to recent Patagonian magmatism. The picture that you see here are some of these Eocene to recent lava flows. They're the dark areas that form the caps or mesas at the tops of those hills seen in this photograph. This picture was actually taken during fieldwork there in 2018. So for those of you not familiar with where Patagonia is, it's at the southern tip of South America at the very other edge of the world. Looking closer, that area inside the red box is what we see here. And there are several geologic features I'd like to draw your attention to. First of these is the Chile Rise. This is a mid-ocean ridge spreading center. And what we can see here is that the Chile Rise runs into the Chile Trench, which is a subduction trench, here at the western edge of South America. This has been ongoing since about 16 million years ago. So multiple segments of this Chile Ridge have been arrested against the continent here, forming this volcanic gap. So the arc volcanoes of the Andes Mountains have shut down and the areas are uplifted, and you can actually see that. Evidence of that is these glaciated areas here. And so it's thought that a slab window is forming beneath the continent here, allowing the upwelling of Cenozoic magmas. So here's another look at that in 3 dimensions. So the Chile Ridge segments collide with the Chile Trench, but the slab on this end keeps subducting into the mantle, and then it allows upwelling of the asthenosphere here by this slab window. So material can flow in this void, if you will. This is a trace element spider diagram you might see in a petrology textbook. And you can see that mid-ocean ridge basalt has this downward sloped pattern, whereas ocean island basalt has this upward slope. So now we're going to look at some of the magmas from Patagonia. So here on the left, we see the La Angelita formation. So these are very clearly OIB type magmas, which is interesting given that we might expect mid-ocean ridge type basalt here. And we see that the ages of these magmas do coincide with that slab window period of beginning about 16 million years ago. There's a problem, however, because magmas from the Alma Gaucha formation and the Cerro del Doce formation also have these very enriched, very similar OIB trace element patterns. However, these magmas are from the Oligocene 22 million years ago and the Eocene 37 and 40 million years ago. So here's another look at that. Here in the dark blue, we see this period of ridge collision, and previous dates constrained a lot of magmas erupting in there. However, we have evidence of the eruption of very similar types of magma, much older, and into the Eocene. So one possible explanation that we have, that we're working on for this, has to do with the magma source lithology. So most petrologists assume that the mantle that melts is olivine rich, or what would be considered a peridotite, which you can see on this ternary diagram as the yellow rocks. So normal peridotite melting produces melts, and the olivine that crystallizes from these melts will have a low, narrow, defined range of iron over manganese. However, it's recently been recognized that one possible source of OIB-type magmas is the melting of pyroxenites, and pyroxenites are the rock types shown on the bottom of this ternary diagram. Olivine that crystallize from melts of pyroxenite show elevated iron over manganese. So we've done a study, we've only looked at the La Angelita basalt olivine thus far. However, they have elevated iron over manganese, as you can see in this plot. So up here in this region indicates olivine derived from pyroxene derivative magmas. If they were derived from a peridotite magma, they would probably lie within this field. So this is good evidence to us that there is pyroxenite in the source of these magmas. So we're going to go back to this look, and we think, our hypothesis that we're working on is that pyroxenite heterogeneity has existed since the Eocene. We're going to be testing olivine in the Eocene and Oligocene magmas to see if that is correct. If that is, a slab window is not needed to explain the volcanism there, and only the destabilization of these pyroxenite lithologies and the melting of them is necessary, which can occur without the slab window. So that's all I have for you today. A special thanks to the Space Grant Consortium for funding this work, as well as the Geological Society of America. And a special thanks to all of these individuals that made this research possible. Thanks for coming.